Let's talk about cosmic chemistry. The business of stars is nucleosynthesis, the fusion of different atomic nuclei under conditions of enormous temperature and pressure to produce new elements. Essentially everything in the material world except for hydrogen and helium, which were primordial in the Big Bang, were created in this way.
Welcome back to The Star Cook.
Thank you. Welcome back. I'm Michaela, and I'm here with my very special guest, Mr. Bill Nye.
Thank you, everyone. Michaela, it's so good to be back on the show, and you are looking fabulous.
Thank you. You too.
Oh, thank you, Michaela.
So tell me, Bill, what are we going to do today?
We have here the ingredients to make virtually anything.
Oh, these are different kinds of atoms.
That's right. These are all the different elements, all the different kinds of atoms in the universe. Now, atoms come from stars. Now, take, for example, our planet. Our planet has a lot of iron and silicon, along with many other elements. And our star has a lot of hydrogen and helium. Now, Michael, oh, that's our hydrogen. Almost lost it there. It's okay, everybody, it's okay. Now, Michaela, you and I are 65% water.
Right.
Now, what's water?
H2O.
That's right, H2O. I have some water here, which I prepared earlier.
Well, of course.
And the water is 2 parts H and 1 part O. H2O, water.
So with this here, we can make virtually anything.
Well, actually, no. Because in order to make all these atoms, you need the force of exploding stars and billions of years. But brownies, on the other hand, only take about 35 minutes.
And even brownies are made of atoms.
That's right.
Oh, Bill, this looks fabulous. People, it looks fabulous, doesn't it?
Oh, thank you. Here, Michael, you please have the first one.
Oh, thank you. Oh, delicious. We'll be right back.
Thank you.
Now people say, why make observations of stars? Why look into space? Are you kidding me? It gives you a perspective of where you are in the universe, of what we do all day. I mean, what are you trying to make some kind of joke? I mean, we are made of the same material as stars. Stars, you, me, the camera, the television you're watching, everything made of the same stuff that stars are made of. So you have to study stars in order to understand what we're made of, for crying out loud.
Whoa.
Low-mass stars, like the Sun, and a little more massive than the Sun, can go one step beyond helium to make carbon. This is a critical step in the fusion process because, of course, biology would not be possible without carbon. And it requires 2 extraordinary tricks, coincidences of nuclear physics, if you like. You might imagine, as with fusion of helium from hydrogen, that you could do this in 2 simple steps, by taking a helium nucleus, fusing it with another one to make beryllium, and then adding a third to make a carbon nucleus. But it doesn't work this way, because beryllium, for reasons of nuclear physics, has an incredibly short decay time. It's radioactive and disintegrates in a trillionth of a second or less. That means that inside a star, when 2 helium nuclei fuse, the result, the beryllium nucleus, disappears almost as quickly as it's assembled, disappearing like sand through your fingers. And the star cannot make carbon that way. The way the star makes carbon is by a much rarer triple collision, which instantly creates carbon from 3 helium nuclei arriving in the same place at the same time. It turns out that this process would be vanishingly rare, leading to essentially no carbon in the universe, if it weren't for a nuclear resonance state, first noticed by Willie Fowler 60 or more years ago. This nuclear resonance state increases the probability that the triple fusion will take place and means that we actually have carbon in the universe. But the scarcity of the triple collision, nonetheless, means that carbon is hundreds of times rarer than hydrogen and helium, the most abundant elements. In general, as we move up the fusion chain, higher and higher temperatures and pressures and densities are required to generate heavier and heavier elements. To make hydrogen into helium requires overcoming the repulsion of two hydrogen nuclei, protons. But to make carbon from helium nuclei means we have to force helium nuclei with double the electrical charge, and therefore 4 times the repulsion, to get close together, requiring correspondingly higher temperatures. Carbon is a critical ingredient in this story, and as we know, and in this video from Linda Williams tells us, carbon is a girl's best friend.
A lithium dose just might cure your depression, but carbon is a girl's best friend. And gold may be grand, but it won't start a fire in your barbecue, or put the toot in your choo-choo, 'cause life on Earth is carbon-based. It came here on rocks from outer space and formed organic compounds till the carbon cycle went round and round. Carbon is a girl's best friend. Well, there may come a time when you need to do some squeezing. Carbon is the world's hardest friend. And there may come a time when a substrate is needed to deposit your film on. Just sputter it on a hot diamond, or if you have some lube and to do, then graphite is the allotrope for you. Or if you're into ages, then carbon-14 can date it. Carbon is a girl's best friend. Well, I've heard of attempts to make hard carbon nitrides, but diamonds always win in the end. You know they do, darling. And I've heard that we need to find something much cleaner to put into our cars, or else we won't get very far, 'cause time rolls on and supplies will be gone of diamonds, coal and petroleum. But nanotechnology can build anything with fullerenes. Carbon! Carbon, yeah! I don't mean hydrogen, but carbon is a girl's best friend. Best friend.
If we consider the full evolutionary path of a low-mass star like the Sun, and this of course includes the story of our Sun, it goes through several phases. The long main sequence phase, 10 billion years long for the Sun, then the star reconfigures to a new state, starting a new energy source, releasing a large envelope and having a collapsing core. This is the red giant phase. In our Sun, when this happens, the outer envelope will expand past the orbit of the Earth, perhaps to Mars, engulfing the biosphere and frying it. If life still exists on Earth billions of years from now, this will probably be the end point. Thereafter, the Sun goes through an unstable phase, ejecting much of its mass into space as a planetary nebula, while the remaining core shrinks. With no new fusion process possible, the core gradually cools as an ember forever. This final state for the Sun is a white dwarf. Since most stars are like the Sun or even lower in mass, this is the fate of most stars. So most of the stellar remnants in the universe are expected to be white dwarfs. If we look at this picture, such as taken with the Hubble Space Telescope of a planetary nebula, we can see both parts of this fate, which awaits the Sun. The sloughing off of layers of gas out into space where they're heated up and glow brightly, and at the center, a a cooling ember, the white dwarf. For stars, mass is destiny. For stars, the mass of the Sun, up to about 1.5 times the mass of the Sun, the battle between gravity and radiation is, as always, won by gravity, and what's left behind is a compact core called a white dwarf, a cooling ember of a star. Only certain heavy elements can be created in stars like the mass of the Sun, up to about carbon. Heavier elements depend on more gravity and larger mass.